Good day. My name is Kuganeshwaran and I like Krishna. Today, I would like to present about the instrumentation system for the measurement of weight from 0 to 5 kg. So let's proceed with the introduction. So this is the introduction where a weighing scale is used to determine the weight of objects or persons. Weight is measured on weighing scales and balances by the amount of force applied to the load cell. The result is then converted to mass and displayed in various mass units. Technical and digital measuring skills are available nowadays since both are very effective. They come in different form of sizes, designs and styles, with the most important feature being that they are becoming more technological. Some weighing scales are extremely light, whereas others are considered heavy due to their sizes. One major difference between these two is that an analog weighing scale uses dials to display weight, but a digital weighing scale displays weight in digital form. So let's go for the project background a bit. So here's the objective of this experiment where we have to design and develop an instrumentation system for the measurement of weight from 0 to 5 kg. Besides that, we need to calibrate the instrumentation system that we make. Furthermore, the accuracy of the developed instrumentation system measurement needs to be investigated. So as we see in the figure below, it's the element of instrumentation system. So let's go a bit further on that. So, there are several elements needed in an instrumentation system in order to obtain an accurate display such as sensors. In our case, the sensors are low-tau, variable conversion elements, which is the transducer, signal processing, signal transmission, and signal recording will be under Arduino. The major element in any instrumentation system is the primary sensor, which is again is our load cell. It is in direct touch with the process being monitored and produces an output that is dependent on the variable being measured. For instance, primary sensors are a liquid in glass, thermometer, thermocouple, strain gauge, and so on. This means sensor is also comprehensive measurement system. It's a measuring system. However, the sensor is the only part of a measuring system. Whenever a main transducer's output must be transformed from one form to another, variable conversion elements are more convenient to be used. The transducer is a combination of the main sensor and the variable conversion element. Now let's go to signal processing. Signal processing exists to enhance the quality of the measuring system output in some manner. The electronic amplifier is a highly frequent sort of signal processing device. It amplifies the output of the main transducer or variable conversion unit, hence increasing the sensitivity and resolution of the measurements. So, in some measuring system, it incorporates additional component to transport the signal to a distant location and to display or record the signal if it is not automatically fed into a feedback control system. Signal transmission is required when the output of the measuring system is seen or used distant from the original transducer. So here's the more or less about the elements of instrumentation system. So for this particular project, we have designed measuring scale upon 0 to 5 kg of measurement as been assigned to us. In the next slide, we will go into the instrumentation system design and I'll explain about it more further. So as seen in the slide above, it's the instrumentation system design. So on the left hand side, the figure shows the uh, dual voltage follower and which is connected to an amplifier with a resistor of R1, R2, RF, and RG. RF is the feedback resistor, and then V1 is connected to a first voltage follower, and V2 is the second voltage follower, which give us voltage supply to the uh, differential amplifier. So let's see what is voltage follower actually. The voltage follower is also known as a buffer amplifier, unity gain amplifier, or isolation amplifier. It's an op-amp circuit whose output voltage is equal to the input voltage. Hence, a voltage follower op-amp does not amplify the input signal and has a voltage gain of 1. The voltage follower provides no attenuation or amplification. It only buffers the system. Thus, the voltage from, let's say the voltage of V1 is 10, then the voltage at the input of the differential amplifier is 10 as well. It's just with a unity gain. That is what we meant by the voltage follower. So on the right hand side, it shows the formula of differential amplifier, where in order to get gain formula is V out over V in. V in here for a differential voltage differential follower is V2 minus V1. We just get where the supply is from the voltage follower. So the gain itself is Rf over R1. So in this case, the gain obtained or the gain designed by me to build a measuring scale is 220 kilowatt, where RF is 220 kilo ohm, and R1 is 1 kilo ohm, which when we divide or calculate it, it will give us a gain of 222. Next, so here, shown here is the real view of signal conditioning using breadboard. So the first the first arrow here shows the voltage follower, second is the differential amplifier, and the third is a voltage follower as well. Sorry, there is a mistake here. So it's a third is a voltage follower as well. So as you see, the first R1 is connected to the first voltage follower, which we give which we accept as its V1, where the supply is coming from the load cell. Second, the RF is connected to the differential amplifier, and then RG is connected to the ground, whereas R2 is connected to the second voltage supplier, second voltage follower, which is V2, is the second voltage supply to the differential. So here you see above, this is a block diagram or more or less like algorithm. So first, power supply. Our power supply is 9-volt battery. And then as we connected the 9-volt battery, it will be connected to the load cell as well, because load cell have few wirings which I'll explain later. Now let's see the block diagram. 9-volt battery is connected, and then it will flow to the voltage follower, uh, and then it will flow to the differential amplifier, and then it will go to the voltage follower again, which is the second supply basically. It's a dual voltage follower, and then from the output of the differential amplifier, it will give a reading on the Arduino, and there will be a serial monitor and Arduino idle app, I mean software, sorry, and then it will show the readings or analog reading of the voltage, and then the analog, I mean the weight value that we desire. So here's the wiring of the diagram. This is basically the diagram inside the strain gauge of the load cell. Red represent the positive input, green represent the output, which will be connected to the first voltage follower, and then black is basically a negative input, which will be connected to the second voltage follower. For white output will be connected, sorry, input on black color will be connected to the negative terminal of the battery, while the red input will be connected to the positive terminal of battery. The green and white wires will be connected to the voltage follower. It doesn't matter at which order we connect, it will give a same reading, similar reading. So this is the Tinkercad drawing of the signal condition circuit. As we see, battery will be connected, positive will be connected to the positive terminal, and negative will be connected to negative terminal. So the first op-amp is known as the first voltage follower, and then the second one is known as this differential amplifier, following with the second voltage follower. And then as you see in the wiring here, from the load cell, the red wire will be connected to the positive terminal, the black wire will be connected to the negative terminal, while the green wire will be connected to the inverting terminal, sorry, non-inverting terminal of the voltage amplifier, as well as same goes to the white wiring. So this Arduino, there is an A not input, and then there will be a ground, sorry, earth wire. So this earth wire will basically give a ground value for the, I mean, it will make the particular breadboard or this particular slot will be a ground value, which will connect, which will ease or which will complete the connection of the breadboard for RG, because basically we need a ground wire in order for a differential amplifier to. So the video just now shown the calibration process, the sample calibration process for 0.5 kg. So as you see here, the step size of the mass to be calibrated is 0.5 kg. Each the consequent 0.5 kg will be recorded, and we will take five reading of five reading of analog, and then we will like take the average value to gain the maximum functionality of this calibration chart. So on the right hand side is the calibration graph where we need to obtain the gradient of the graph and then the y-intercept so that we will develop a new Arduino coding to reduce the error uh, for the load cell to function. Seen in the video before, it's how the calibration process works, or is a sample calibration of 0.5 kg. As you see the serial monitor, it will show what is the error, what is the actual value, and then what is the output value. So for here, for example, in the column of the table, the column is first column is actual rate, and the second column is output of the Arduino reading. So let's say, for example, 0.5 kg, we can get 0.47 kilogram, which is quite not to say very accurate, but it's quite accurate where we have already minimized the error to negative 0.02 to negative 0.04. So the reading is more or less linear. As we see on the graph of output rate against actual rate, we obtain a linear graph with the equation of y equal to 0.9987x minus 0.286x with a gradient, linear gradient almost approach unity, and a y-intercept at negative 0.0286, which is almost approach the value of zero. So the relationship is output weight is directly proportional to the actual weight. So it gives it means the linearity of the graph represent the accuracy. So it means our weighing scale is quite accurate where we minimize the error between the fluctuation points. Next, let's see the fabrication. So as you see, this is before fabrication. This is what we get before fabrication. Before we actually create any enclosure for this particular weighing scale. So as you see that the signal conditioner is connected to a PVC wire connectors, 9-volt batteries, dumbbell weight with 0.5 kg each. So meaning here is 2 kg here. Serial monitor is a display, and the load cell is carrying 5 kg load. I mean 5 kg load. So this is after fabrication. It looks more neat, and then it is portable where we can carry it anywhere we want, and then it is more organized where even there is a high falls or we applied falls on the basement, it won't crack or something because it's made up of the polycarbonate plastic, which is very the toughness of it is very high, and then the tensile stress of it is very high, and more importantly, it can last long and can resist with too much of heat. When you're exposed to too much of heat, like sunlight or near to any flammable or maybe heating of like more than the normal room temperature, then it can actually resist that type of heating because it's a good heat conductor. So that is all from me. Thank you very much.